All right, so 3.33. So this says photosynthesis makes use of visible light to bring about chemical changes. Explain why heat energy in the form of infrared radiation is ineffective for photosynthesis. All right, so we know photosynthesis ultimately is the process by which plants convert carbon dioxide and water that they get into sugars. A variety of sugars, including like cellulose and glucose and other carbon, hydrogen, oxygen containing molecules. So this process occurs with an increase in potential energy, because the arrangement of protons and electrons in carbon dioxide and water is a more stable arrangement. In carbon dioxide and water, the way that those atoms are bonded together and the electrons are arranged around them, the electrons are able to form pretty strong attractions to the carbon, oxygen, and hydrogen nuclei. If I break up the arrangement of atoms and electrons in CO2 and water and reform it in the form of a sugar, the electrons are not as stable. They're not able to get as close to the nuclei as they were before. So it's kind of the same. It's very similar to pushing electrons from like maybe the first energy level to the second energy level. Right? I'm going up in potential energy because I have to take the electrons away from something they're attracted to. When I break attractions, even if I reform them, if the new attractions I reform aren't as strong as the old attractions, the overall net situation there is that I'm breaking some of the attractions. That requires me to put energy in. Energy has to be absorbed. So plants, we know, can't do this without light. I've got to put in light. Plants may, in a different environment, have evolved to do this reaction without light. Maybe they, in a different environment, could have evolved to do it with heat energy or some other electrical source of energy.
Probably ground floor of the rainforest. It's really dark down there. Probably the heat, the humidity. Maybe.
Yeah, well, it would be a different process. I mean, it wouldn't be photosynthesis if they're using some other form of energy, but the overall process of converting, CO2 into sugar, it could have evolved differently, depending on the different situation. But what our plants on Earth use to do photosynthesis is light. And so the question is basically saying, why can't heat in the form of infrared radiation, so I don't know why they describe it that way, infrared radiation is light. It's not heat. Hot objects convert some of their kinetic energy, right? If you have a hot object that's at a high temperature, that means the particles are moving relatively fast. They're vibrating a lot if it's in a solid state. So if it's hot, if it's a high temperature, over time, some of that motion will naturally be converted into infrared radiation. And so the particles, as they're cooling down, one way for objects to cool down is for them to collide with other things and transfer that motion through a collision to another object. But another way for things to cool down, we saw this in one of the simulations a little bit, is if spontaneously that motion, that kinetic energy of the particles gets converted into light, it can be released as a different form of energy. And when light is released from hot objects, usually it's in the area of wavelengths that are in the infrared range. So basically the question is here, why can't I use infrared light to grow plants? Why won't plants survive and use infrared light to convert CO2 and water into sugar? Any idea why they can't do that?
It's the the one particular light is just right or not.
Yeah.
I remember reading this.
Yeah, right. So it has to do with the type of light and ultimately how much energy that light has, right? So what we know is if we want to break up CO2 and water, there are certain strength of attractions holding the electrons and the atoms together in that form, in the form of CO2 and water molecules. If I need to break those up, that requires me to put in some specific amount of energy. And if I don't apply enough, I'm not going to be able to break up those bonds, right? So we talked about the threshold energy in atoms, right? If I've got a hydrogen atom, there's an electron here. There's a certain threshold. I have to overcome this attraction if I want to knock the electron out. So that's a threshold required to overcome that attraction. So it's not just the attraction between an electron and its nucleus that has threshold energy. Any process that requires energy will have a certain threshold required, right? So if I want a rocket to break free from Earth's gravity and go into outer space, there's a threshold. I need to have enough fuel to get that rocket to break whatever the force of gravity is that's acting on it. And so when I have CO2 and water combined together, bonding together, I need some energy to overcome the strength of those bonds. And when we look at the high energy to low energy scale, which involves short wavelength light like gamma, oops, there's two M's there, and X-rays, then UV, visible, then I get to IR before micro and radio. So IR is on the relatively low energy side because it has long wavelengths. So I can hit plants with as much IR radiation as I want, but those waves are just too far apart, and the packets of energy are too far apart. None of the waves, no matter how many of them I hit the plants with, none of them have enough energy to overcome the water and CO2 bonds, so the plants can't then rearrange those molecules into different usable form by the plants in the form of sugars. So it's very similar. The idea behind this question is very similar, which is why they put it in here. It's very similar to the idea behind the photoelectric effect. Can I use light to break up attraction? Yes, but the light has to have enough energy to overcome whatever strength of attraction there is between those particles. And so I can't use low energy light to break up strong attractions. If I have a strong attraction, there has to be a certain strength in that light to break that attraction up. So for plants, they have that chloroform, right? That's what makes them green. Chloroform absorbs visible light. What wavelength of light, well, not maybe what wavelength, but what color of light does chloroform absorb? Well, the leaves appear green, right? Does that mean they're absorbing green light? No, that means the green light. So there's white light coming from the sun. The white light has all the colors in it. When the white light hits the leaves, some of the light's absorbed, but the green is not, because the green is reflected to your eyes. That's why you see green. So it's absorbing mainly red. The opposite of green on the color wheel is red. So it's absorbing mainly red and like reddish orange and yellow. Those are the colors that the leaves are absorbing. So in the fall, when the chloroform breaks down, it's not present, then you see the red and yellow now. You don't just see the green. But the point there is the photosynthesis requires the chloroform to absorb that specific amount of energy, and then it uses that energy and converts it into potential energy as it breaks up the attractions between the CO2 and water. But if you don't have enough energy in the light, it's not going to cause that reaction. There's a threshold. So if you use UV light or light that's higher in energy than is necessary, Well, it would depend on the specific situation. Sometimes, if there's a threshold and you put more than enough energy in, you'll be able to make the process happen. And then often the products of that process will have more kinetic energy because you put extra energy in. Often that will be converted to kinetic energy in the end. Sometimes, though, if you have a kind of a fragile molecule like in plants, those molecules in plants are kind of complex and they're kind of fragile. So if you hit those with too much energy, you might just break the molecules up, which, that's not what needs to happen for the plants to convert that energy into chemical reaction. Other questions? Yes?
I don't know what question it is. It's shining two different lasers from a metal object. The yellow laser and the blue laser. Two different lasers.
3.51, some copper-containing substances emit green light when they are heated in a flame? No. 39? Okay. 39. A photoelectric experiment was performed. So that's the one where you have the two metals with different charges. The one metal has a negative charge on it. You hit it with light, and if the light has the threshold energy, it'll knock electrons out. They'll fly through space and go to the positively charged metal because they're attracted to it. So we want to perform that experiment with a 450 nanometer blue light and a 560 nanometer yellow light. So before we get any further, if we're doing the experiment with two different forms of light, we want to make sure we have a decent understanding of what the difference is between these different forms of light. So if I just give you the wavelengths, what can you already say about those two different colors? Right, if I give you the wavelengths, the one with the shorter wavelength is higher energy and also higher frequency. But the energy is the important thing there, especially in the photoelectric effect, right? Because that effect.
I thought you were talking about distance away from.
Oh, okay, right. Okay, so right, that I could see how that would be confusing. If you're talking about a nanometer distance between the laser and the object, that shouldn't matter because the light should be able to travel through a vacuum, without diminishing its power.
I'm sorry, what was that line again that was pointing to the 450 AM? That line you drew with a little TB10?
That's a wavelength.
Wavelength.
Yep. Yeah, so just to finish the question, the idea here is if you have the photoelectric effect and you hit the metal with a higher energy form of light, as long as it meets the threshold, you'll see electrons coming out of that object, right? So basically the light is used to break the attraction the electrons have to the metal, and when I use a higher energy form of light with a shorter wavelength, I'm more likely to be above the threshold. If I'm above the threshold, electrons will start coming out. If both wavelengths, so let's say both of these are high enough energy to be above the threshold. If they're both above the threshold, they're both capable of knocking electrons out of that atom. In that case, whichever has more energy, when it hits the electrons and breaks the electron's attraction to the atom, that extra energy usually causes the electrons to have more kinetic energy as they're flying away. Right? So the light energy that hits the atom, some of that light energy is converted to potential energy because the potential energy increase occurs when I take the electron that's close to the nucleus and knock it out of the atom. If the light energy wavelength is just exactly equal, and the light energy is equal to the potential energy difference for the electrons being in the atom versus being out of the atom, then it will just knock the electrons out. But if there's more energy in addition because the wavelength is smaller, then it will knock the electron out, and the extra energy will go into the electron and cause it to fly through space faster with more kinetic energy. So which light would generate more electrons? Well, in that case, there really shouldn't be a difference. As long as both wavelengths are above the threshold, the one that I shine more light at, so as long as these are both above the threshold, the intensity of the lamp, or the time I use the lamp for, will be the factors that determine how many electrons come out. The wavelength isn't really a factor there. Which light would eject electrons with the greater kinetic energy? Well, that would be the one with the lower or shorter wavelength, because some of the light energy would be converted to potential energy to break the electron's attraction to the nucleus, but some would then also be converted to kinetic energy. So then the last part's a little tricky. It says, assume that the same total amount of energy is delivered to the metal surface by each laser. And okay, I see. We're supposed to assume that before we answer the above question. Assume that the total amount of energy delivered is the same, and that the frequencies exceed the threshold. Okay. So they're both exceeding the threshold. This is a cool question. All right, so let me maybe draw a picture so we can get a visual of this. Okay, so we've got one metal here, one here. We connect that to a battery with a negative end and a positive end. Electrons flow onto this metal, and they're attracted to the nuclei of the metal atoms there. They flow away from this metal, creating some positive charges. Then I'm going to use light to hit this, and if the light is above the threshold, which the question is telling us that both these frequencies are above the threshold, that will knock this electron out of there. What the heck? That was crazy. That will knock this electron out of there, and it'll fly to the other side. So both wavelengths have the energy necessary to overcome that attraction. So when the question says that the 450 and the 560 are both shined on the metal with the same energy, that might seem confusing, because we learned that the shorter wavelength has more energy. So if I want to shine this light at the metal and also shine this light at the metal and have both lights supply the same amount of total energy, how could I do that if one has a shorter wavelength?
Placing the metals to reflect better?
Well, there shouldn't be any reflection of the light. The light should be absorbed by the metal, and that energy would cause the electron to break off. But the key thing here is this one has more energy because the packets are closer together, and if I shine that for 5 minutes, I get so much energy applied to the metal. So this is lower in energy because the wavelengths are farther apart. I have to use it for a longer period of time. So if I'm using this one for a longer period of time, to get the same amount of energy eventually transported into the metal. Right? So that means we have to modify our answer to the first part of the question. Which light would generate more electrons? If they're both at the threshold, they would generate the same number of electrons, but since I'm shining this for a longer period of time, to get the same amount of energy, then this one would knock out more electrons total. because I'm using it for a longer period of time. Right? So if I'm shining this light on the metal, they're knocking out the same number of electrons, and then I turn one lamp off and keep the other lamp on. It's going to continue to knock electrons out for a little while. But this one is more energy, so while I'm shining it, when it hits, it has enough energy to knock the electron out, plus it has more energy, so the electrons come out with more kinetic energy. They come out with more speed.
So, but at the point, like right before the more energized light turns off, it's exactly the same. And then once that light turns off, it increases only because the light comes on.
Right. Yeah, so overall, both lamps have supplied the same amount of energy. The 450 lamp was on for a shorter period of time, and while it was on, it knocked so many electrons out, and those electrons came out with more speed. So that lamp supplied the energy, to potential energy difference necessary to break the electrons' attraction to their nuclei, plus some kinetic energy to make the electrons come out with more speed. That same total amount of energy supplied by the other lamp was just used to knock more slow-moving electrons out. So all of that, for the most part, was used to go into potential energy, not so much into kinetic energy. Other questions?
The 5060N is shining. That's the only one.
Well, the question says they're both. Really, the question is two different experiments. One experiment where you're shining the 450 nanometer light, and then another experiment where you're shining the 560 nanometer light, and you're comparing the results of the two experiments. Say 351. So 351 says you have this copper-containing substance emitting green light when they are heated in a flame. And so let's first make sure we understand what's happening there and why. So we've got this substance. We're going to heat it. I don't know how to draw a flame, so I'm just going to put heat down there. The substance heats up, and it spontaneously creates light. Why? So if it's, yeah, so that's a little bit tricky. So one other detail is it says that it's emitting green light. So usually the colored light is not just the heat or vibration converted into light energy. That usually produces infrared light. Although if it's a really high vibration, it could produce some colored light. Mainly, though, in the other examples we talked about, in the situation where matter is emitting light or producing light, it's usually because you've got the atoms. So in this case, they'd be copper atoms, with a positive charge in their nucleus, and then the electrons that are present are in a certain energy level. They get kicked up to a higher energy level. Then, when they relax back down from a state of higher potential energy to lower potential energy, that difference in potential energy is converted into light energy. Right, so that was the line spectrum, the emission spectrum we saw with the hydrogen last time. Right, so what happens is, if some of this heat is used to overcome some of this attraction, the electron moves away. That doesn't produce any light. But when the electron relaxes back down and goes from high energy to low energy, that difference in energy has to go somewhere. It can't just be destroyed. So that's emitted in the form of light. So that's what is probably happening here. So how would you determine whether the light is of one wavelength or a mixture of two or more wavelengths? Well, that would be a situation where you would use a prism. Right, so In that example of the hydrogen lamp was heated up. This process occurs where the electron gets excited and then relaxes back down and releases that light. All the light comes out. It's more than one wavelength. But when it hits a prism, the prism will bend different wavelengths at a different angle so you can separate the different wavelengths that are coming out and see them individually. So you would need to use a prism basically to see if that light coming out is one wavelength or multiple wavelengths. Probably it would be multiple wavelengths because depending on the amount of energy you put in, it'd be pretty likely that that amount of energy, right, even if you heat something up, not all of the atoms are going to absorb that energy in the same way. Some will be moving faster than others, and so some of the atoms might have their electron get excited to a higher level, and then when it relaxes back down, there's multiple ways that it could relax back down, and each of those different ways would release a different wavelength of light. Any other questions? .1. So this is the visualizing chemistry section on page 101. So the question 3.1 says, which of the following best explains why we see only 4 lines in the emission spectrum of hydrogen? So I would probably modify that question and make it a little bit more clear. And it would say, why are there only 4 lines in the visible region of hydrogen's emission spectrum? That word visible is kind of important. They've left it out there. So choice A says hydrogen has only 4 different electronic transitions. Is that correct? No, that's not correct. Right? When we think about hydrogen, for hydrogen, if we think about plotting the potential energy, where at the bottom I have low potential energy, and as I increase I have high potential energy. For the hydrogen, when let's say its nucleus is here, when the electron is close to the nucleus, that's a low potential energy, right? So that would be like energy level 1. We call that n equals 1. I can move the electron from there up to the next energy level, n equals 2. Right? So that's one possible transition. Or I could move it up to the next level. That would be like n equals 3. Or the next level, which would be n equals 4, etc. 5, 6, 7. Why does the energy, the potential energy difference between the levels get smaller and smaller as I go farther out from the nucleus?
The further it gets away, the less the attraction.
Yeah, if it's already, like, when it's close to the nucleus, that attraction between the opposite charges is strong. It takes this much energy to break that attraction. But if it's already out here, when the charges that are attracting are already a greater distance, there's not as much of an attraction between them. It doesn't take much energy to push them a little bit further apart. So the farther they are apart, the less energy it takes to push them one more level away. But what we learned is there are lots of levels. How do we know there are lots of levels? Experimentally. Right, we just observe all the light that comes out, and we see there's more than 4 different levels. When the electron gets excited, it could go all the way up to n equals 7 or 8. And once it does, let's say my electron gets bumped up to here. It could go down just 1 level, it could go down 2 levels, it could go down 3 levels, 4, 5, 6. once it gets excited and it's at this level, it could do any number of things. It could relax to any one of the levels below it. It doesn't always have to go all the way down to the level where it will go and be most stable. If it's here, it could go down to 4 first, and then from 4, it could go to 3, or from 4 it could go to 2, and then from 2 it could go to 1. Eventually, it will end up in level 1 where it's most attractive, but it won't necessarily go there right away. How do I know that? Because experimentally, I see light coming out with wavelengths that are equal to all these different energy differences. Right? So when I excite the hydrogen atom, I see a wavelength come out that's equal to this small difference in energy between 6 and 7. But that wavelength is not in the visible region because it's a small amount of energy. It's like in the infrared region. It's too small an energy to be seen with the visible eye. But I also see an energy from 7 to 2. The difference in energy between n equals 7 and n equals 2, that quantity of energy, potential energy, when it's converted to light, is in the visible region. So if you want to say that hydrogen only has 4 different electronic transitions, that's not correct. There's many, many different electronic transitions because when I excite the electron, it could do any number of these combinations of transitions on its way back down to n equals 1. If you want to say that B is correct, only 4 of hydrogen's electronic transitions correspond to visible wavelength, that is correct. Every possible transition here either has too much energy or too little energy, except for to be in the visible region. The visible region, the region of light that you can actually see with your eyes, is a very, very narrow part of the entire spectrum of light. You can't see gamma rays or X-rays or UV light. Your eyes cannot detect infrared light, microwaves, or radio waves. You can only see light when the wavelength is between about 450 and 700 something nanometers. That's a very small section. So only a few transitions here have the exact amount of energy that will be converted to light to produce light in the area that you can see. Only 4 of them. That's why you only see 4 bands of 4 specific colors. So B is the correct answer there. Yes?
What causes our electron to relax?
It's attraction to the nucleus because opposite charges attract. So this is the line spectrum experiment. In the line spectrum experiment, I'm only using enough energy to excite the electron to a higher energy level. It's different from the photoelectric effect experiment. In the photoelectric effect experiment, I'm seeing it about how much energy of a threshold there is to knock the electron completely out of the atom. Once I knock it out of the atom, it's not close enough to feel the attraction. It won't necessarily come back in. But if I keep it in the atom just by taking it to a higher level within the atom, then it will fall back down until there's some combination of relaxations until eventually it ends with 1. And how do we know that? Because we see these light wavelengths coming out that correspond to each one of those relaxation combinations. Other questions?